What if I told you that right now there is a spacecraft orbiting Earth that uses absolutely zero fuel? No chemical rockets, no iron engines, nothing burning, nothing exploding. It moves through space using nothing but sunlight. Sounds like science fiction, right? But it's completely real. It's called a solar sail, and it might just be the technology that takes humanity to the stars. Think of it like this. Imagine you're standing on a frozen lake and someone shines a flashlight at you. You wouldn't feel anything, right? But in space, where there's no friction, no air resistance, nothing slowing you down, that tiny push from light actually adds up. And it keeps adding up, day after day, week after week, faster and faster, with no fuel tank ever running empty. Today on SpaceVidya, we are breaking down exactly how solar sails work, from the mind-bending physics of photon pressure to the ultra-thin materials thinner than a human hair, to NASA's real missions testing this technology right now. By the end of this video, you'll understand why many scientists believe solar sails could be our ticket to interstellar travel. Let's get into it. Okay, so let's start with the fundamentals. What exactly is a solar sail? At its core, a solar sail is a large, ultra-thin, highly reflective sheet, kind of like a giant mirror in space, that catches sunlight and uses it for propulsion. Think of it like this. Just as a sailboat catches wind to move across the ocean, a solar sail catches light to move through space. But here's where it gets really interesting. Wind pushes a sailboat because air molecules have mass. They physically slam into the sail and push it. Light doesn't have mass. Photons, the particles that make up light, are massless. So how on Earth, or rather how in space, do they push anything? This is where Einstein's physics comes in. Even though photons have no mass, they do carry momentum. It's one of the most counterintuitive things in physics. When a photon hits a reflective surface, it bounces off, and in doing so, it transfers its momentum to that surface. And because the surface is reflective, the photon bounces back, which means it transfers momentum twice, once when it arrives and once when it leaves. That double momentum transfer is what gives solar sails their push. Now, the force from a single photon is absolutely tiny. We're talking about 9 micronewtons per square meter at Earth's distance from the sun. That's like the weight of a mosquito landing on your hand. But here's the beautiful part. There are trillions of photons hitting that sail every single second. And unlike a rocket engine that eventually runs out of fuel, this force never stops. It's constant, it's free, and it goes on forever. So if the concept is so elegant, why aren't all spacecraft using solar sails? Well, the engineering is incredibly challenging. Let me walk you through what it takes to actually build one of these things. First, the sail material itself. You need something that's simultaneously reflective, lightweight, and strong enough to survive the brutal environment of space. The material of choice is usually polyimide. You might know it by its brand name, Captain, coated with a thin layer of aluminum for reflectivity. How thin are we talking? These sails are typically 2 to 7 micrometers thick. A human hair is about 70 micrometers. So we're talking about material that is 10 times thinner than a single strand of your hair. Now here's the real engineering puzzle: deployment. You can't launch a giant sail into space fully extended. It would never fit in a rocket fairing. So engineers have to fold these massive sheets down into incredibly compact packages, launch them into orbit, and then unfold them perfectly in the vacuum of space. One wrong fold, one stuck mechanism, and the whole mission is over. This is where the booms come in, the structural supports that hold the sail open. NASA's latest mission, ACS-3, uses revolutionary composite carbon fiber booms that are 75% lighter than previous metal versions and experience 100 times less thermal distortion. Think of it like this. Imagine trying to hold open a bedsheet the size of a small apartment using poles thinner than your finger while floating in zero gravity in temperatures swinging between plus 120 and minus 150 degrees Celsius. That's what these booms have to do. The ACS-3 mission, launched in April 2024, successfully deployed its sail in orbit, about 9 meters per side, roughly the size of a small apartment. And it's up there right now, sending back data that will shape the future of this technology. Okay, so you've got your sail deployed in space, sunlight is hitting it, pushing you forward. But wait, if light only pushes you away from the sun, how do you actually navigate? How do you steer? Can you go sideways? Can you go toward the sun? The answer is yes to all of those, and the way it works is absolutely genius. Think of it like this. If you angle the sail so it faces the sun directly, like holding a mirror flat toward a flashlight, all the force pushes you straight away from the sun. Simple enough. But if you tilt the sail at an angle, the reflected light goes off to one side, and by Newton's third law, the sail gets pushed in the opposite direction. By carefully adjusting the sail's angle, you can redirect the thrust in almost any direction. But the really clever part is how you move toward the sun. This seems impossible at first. The sun is pushing you away, so how do you get closer? The trick is orbital mechanics. If you tilt the sail so the light pressure slows you down in your orbit, you lose orbital energy and you naturally fall into a lower, closer orbit around the sun. It's the same principle astronauts use when they fire retro rockets to deorbit. Slow down and gravity pulls you in. Solar sail engineers control attitude, that's the orientation of the sail. Using a combination of small reflective vanes at the sail's edges, reaction wheels inside the spacecraft, and even something called differential reflectivity, where they can electronically change how reflective different parts of the sail are, creating uneven pressure that rotates the craft. It's like having an invisible steering wheel made of light. Quick pause, friends. If you're finding this breakdown of solar sail technology as fascinating as I do me a favor. Hit that subscribe button and tap the bell icon. We break down mind-blowing space concepts like this every week on SpaceVidya. And drop a comment below. Would you ride on a solar sail spacecraft? I want to hear your thoughts. Alright, let's keep going because the future applications of this technology are going to blow your mind. Now, solar sails aren't just a theoretical concept sitting in some engineer's notebook. They've actually been tested and proven in space multiple times. The pioneer was Japan's Icarus mission in 2010, the world's first interplanetary solar sail. JAXA launched this 14-meter diagonal sail toward Venus, and it successfully demonstrated solar sailing in deep space. It actually flew by Venus using nothing but sunlight for propulsion. That was a historic moment. Then came Light Sail 2, built by the Planetary Society. Launched in 2019, this little CubeSat with a 32 square meter Mylar sail proved that you could do controlled solar sailing in Earth's orbit. It measurably raised its orbit using only the pressure of sunlight. No fuel, just photons. And right now, NASA's ACS-3 mission is orbiting Earth, testing next-generation composite boom technology. The data from ACS-3 is critical because it's paving the way for much larger sails that could revolutionize how we explore the solar system. Speaking of larger sails, NOAA and NASA are developing a massive solar sail called the Space Storm Solar Sail Sentinel, or S5. When fully deployed, this sail will cover nearly 18,000 square feet. That's about 4 basketball courts side by side. Its mission? To park a space weather monitoring station closer to the sun than the L1 Lagrange point, giving us earlier warning of dangerous solar storms heading towards Earth. This could launch as early as 2029. And this brings us to the ultimate dream, interstellar travel. See, the fundamental limitation of chemical rockets is fuel. You need fuel to accelerate, but carrying more fuel makes you heavier, which means you need even more fuel. It's a vicious cycle that physicists call the tyranny of the rocket equation. Solar sails completely break this cycle. No fuel means no mass penalty. You just keep accelerating forever. With advanced solar sails, spacecraft could reach speeds of 100 to 150 kilometers per second, fast enough to reach Jupiter in just 2 years or Pluto in 5. Compare that to New Horizons, which took 9.5 years to reach Pluto using conventional rockets. But the most ambitious vision is Breakthrough Starshot, a project backed by some of the biggest names in science. The idea is to use powerful ground-based lasers to push tiny, gram-scale solar sails to 20% the speed of light. At that speed, a fleet of these tiny probes could reach Alpha Centauri, our nearest neighboring star system, in just 20 years. That's within a human lifetime. We could potentially see images from another star system in our lifetimes. Solar sails represent something profound, a technology where the universe itself provides the fuel. As long as stars shine, solar sails can fly. And that, my friends, is how you sail the cosmos on a beam of light. And that's how solar sails work. From the quantum physics of photon momentum to the ultra thin engineering of the sails themselves to the orbital mechanics of steering with light, all the way to dreams of reaching other stars. Thank you so much for watching this episode of SpaceVidya. If you learned something new today, smash that like button, subscribe if you haven't already, and share this video with someone who loves space as much as we do. I'll see you in the next one. Until then, keep looking up and never stop wondering how it all works. Bye.